The diagram illustrates the basic design of a railgun. A very light rod with a mass of 2 grams and a length of 10 centimeters can move without friction on 2 parallel horizontal rails. The 2 rails are connected to a power supply that can provide a constant current of 3 amps and are located in a perpendicularly oriented uniform 0.05 Tesla magnetic field. On the diagram, show the direction of the conventional current in the rail. In what direction must the field be oriented in order to accelerate the rod to the right? And here's our battery over here. And just if you're not familiar with that little picture, the longer side there is positive, and that little chunky thing that's shorter, that's the negative terminal. What is the magnitude of the magnetic force on the rod? What is its acceleration? What is the velocity of the rod as it leaves the rails over here? And how much time does it take for the rod to reach the edge of the rails? On the diagram, show the direction of the conventional current in the rod. The current leaves the positive terminal of the battery, it's down here, goes like this, and comes back to complete the circuit by entering the negative terminal. So in the rod, it is going in this direction, it is going up. In what direction must the magnetic field be oriented in order to accelerate the rod to the right? Well, if you accelerate it to the right, you need a force to the right. So we use the right-hand rule. The current is to the top of the page inside the rod here. So we put your 4 fingers in that direction. The force must be to the right. So you orient your hand so the 4 fingers are pointing to the top of the page and your thumb is pointing to the right. What happens with your fingers? Well, if you curl them to try and touch your palm, they come out of the page. That gives you the direction of the magnetic field. Another way of looking at it, you don't even have to curl your fingers. Which way is your palm facing when you have your thumb to the right and your 4 fingers going straight up? Well, it's facing out of the page, so the magnetic field is out of the page. What is the magnitude of the magnetic force on the rod? Well, since we have a current, we use the Philb equation. F equals current times length times magnetic field. The current is 3 amps. We've got the length of this guy right here. We want the length of the rod, which is 0.10 meters, times the magnetic field, and we get 0.015 newtons. And the L over here, right, just to remind you again, length of the rod, 10 centimeters. And what did we have to do to that 10? Had to convert it to centimeters. So you move the decimal over 2 places and you have centimeters. Excuse me, and you have meters, of course. 0.1 meter is 10 centimeters. What is the acceleration of the rod? Newton's second law, sum of the forces is ma, and in this case the only force we have moving the rod is the magnetic force. So F sub b equals ma, divide both sides by m, put in our numbers, and note what we did here. Problem gave us 2 grams. To get kilograms, you move the decimal place 3 places over and you get 0.002, and our answer is 7.5 meters per second squared. What is the velocity of the rod as it leaves the rails? Well, we're not given a time here, so this is going to be a kinematics problem, so kinematics without time is the 3rd kinematics equation. So what we're going to do, since they didn't give us any initial velocity, we have to assume it was 0, and we're always free to start our problem at x0 equals 0. So we have v squared is 2ax, where x is the distance it travels, and we want to find the velocity when it leaves the rails. Well, if you look up here, we weren't given that. However, look at the picture. It's not just important to read the words of the problem, you have to look at the picture. Look at this. It tells you that the rails are 75 centimeters long. So in our problem here, we have the velocity is the square root of 2ax. Here's the acceleration we found, and right here, this is the distance it traveled before it ran off the rails, the 75 centimeters. Convert that to meters by moving the decimal twice to the left, and we get the velocity when the rod leaves the rails right over here of 3.35 meters per second. How much time does it take for the rod to reach the edge of the rails? And the edge, of course, is the 75 centimeter. Well, you can either use first or second kinematics, but if you have a choice and you have all the variables you need, go ahead and do the first one. It's easier. So v is v0 plus at. The original velocity is 0, so it's just at. So t will equal the velocity, which we found on the previous slide, the acceleration, which we found a few slides back, and we get 0.45 seconds. And let's see, look at the units. We have meters per second over meters per second squared. Meters cancel out, and then this s squared over here comes up to the top. So we have s squared over s, and we get seconds. So that's good.